So if we're given this ladder sliding down the wall situation, and let's say this point of the ladder is point A, and then the base of the ladder is point B. It looks like this ladder here is sitting in the stand, which is probably not the most stable surface. So it shouldn't really be surprising that it starts to slide. So we have, say, center of mass of the link is here. And so if point A starts to slide down here with speed VA, then point B will slide back with speed VB. And let's draw a triangle so we have a good picture. And length of the ladder is L. And so we have the Y component here, and we have the X component here. So the X component is how far away the base is from the wall. And then the Y component is how far away the top is from the floor. If we're given velocity of point A, let's say VA equals 0.5 meters per second constant. And then the length of the ladder, L equals 5 meters. And we need to find velocity of point B, omega of the ladder, acceleration of point B, and angular acceleration of the ladder, alpha. So the one thing that we need to know that we haven't been given yet is what is the starting position of the ladder? So what is the current position that it's at? Because even though VA is a constant value and the length is a constant value, the velocity of B, the angular velocity of the ladder, those are not necessarily going to be constant because they're going to depend on the position of the ladder. So when the ladder is right smack up against the wall, well, in that situation, it wouldn't start sliding at all if it was really right up against the wall. But if it's at that point and then it starts to slide down, then for whatever VA is, B is going to be going at a very, very fast speed. But then by the time A hits the ground, B is essentially going to be stopped because once the ladder hits the ground, like B cannot progress to the right any further than it was. So at the beginning, at the most vertical position, VB will be greatest. And at the most horizontal position, VB will be lowest. So VB is not a constant, even though VA is a constant. And then if VB is not a constant, then probably omega is not a constant, and AB and alpha, and none of those are constants. So we need to be given a starting position. And we'll make it, if L is 5 meters, we'll make this easy and say it's a 3, 4, 5 triangle at the start. So we aren't given a theta, we'll just give it a 3, 4, 5 triangle. So we could calculate a theta if we wanted to. But we'll see if we need to do that or if we can just use ratios of the sides. Okay, so the order that we need to solve things in is really we'll probably end up having to get omega first before VB and alpha before AB. But let's start off by labeling what types of motion or what type of motion does the ladder have? Is this translation, rotation, or general planar motion? Okay, so Susan says it is general planar, and yes, that is correct. So one end of the ladder, point A, is translating vertically. Point B is translating horizontally. So the ladder doesn't have pure translation because the ends are going in different directions that are perpendicular to each other and not collinear. So this is general planar motion because we know that the ladder is also rotating. Okay, so now that we've identified the type of motion, then we'll need to start writing equations. And this is one where instead of using those lengthy formulas for general planar motion that we have discussed, we will just start out with position and start taking derivatives until we get to acceleration. Or first position to velocity and then to acceleration. So we'll just write that here. Take derivatives. So we know that, I'll say x equals, or v, so vb equals dx dt, and va equals dy dt from the picture. So we'll use that, and then we can also use our knowledge of translation to rotation. So we know that v equals r omega, a equals r alpha. So we'll start out on part one, we'll start out with position. So we need to write equations for position, and then we'll be able to take those derivatives to get velocity and then acceleration. So the current position we're shown here is the 3, 4, 5 triangle. But we need to write position in terms of x and y so that we can get to the velocity. So dx dt is x dot, dy dt equals y dot, and this here, v equals r omega, which is r theta dot. So we'll just write that to remind ourselves of a different form of expression for it. So in here, our equations for position will have x equals length of ladder, and if this is theta, we have L cosine theta for x, and y equals L sine theta. So these are really just the standard equations for the triangle. So now step 2, we have to take the derivative for velocity. So if we go ahead here and do a time derivative, then we'll get x dot and y dot. So L is a constant. That's good. Theta is what changes. So we're going to use chain rule here. Derivative of cosine is minus sine. So we have negative L sine theta. And then because of chain rule, the theta dot pops out. And now the y is going to be real similar. So derivative of sine is cosine. So we have y dot equals L cosine theta. And that will also be times theta dot. So just to sort of think about the units of it, if x and y are in meters, then x dot, the velocity is going to be meters per second. And so we have here a meters from the L and then times a radians per second. Radians vanish, and so we get meters per second. And we know that this x dot, speed at which the x direction is changing, is the same as VB. Because VB is how far or how quickly that point of the ladder is moving to the right, which is the same as how quickly x is changing. And then the y dot equals the a for similar reasons. And VA, we need to make a note here. VA is pointing down, so this should be a negative 0.5 meters per second. Now VB is going to be positive because VB is going to the right. So this is the positive x direction to the right, and then negative y direction would be going down. Okay, so we've got these two things. Now theta dot is the same as omega. So I'm going to go ahead here and erase the theta dot and just write omega because that is what the problem has called it right here. Okay, so now we have two equations, x dot and y dot, and we have two unknowns, which are omega and VB. Now theta is also an unknown, but theta is pretty easy to solve for. However, we can just use ratios here. So we know that sine equals opposite over hypotenuse. So sine theta equals 4/5 from this triangle. And cosine theta is adjacent over hypotenuse equals 3/5. So it'll be easier, rather than find theta, we'll just plug in these ratios. So we will take this y dot equation because we're given VA, and we'll solve out for omega. And then we'll take omega, plug into the VB equation, and solve for VB. So going down here, we'll have 5 times cosine theta, which is 3/5, times omega equals VA, which is negative 0.5 meters per second. So now this cancels. Omega equals negative 0.5, which is really 1/2, times, or also divide by 3. So omega equals 1/6 radians per second. And this is negative. So if you have 0.5 divided by 3, then you have 1/6. So we got omega. So now we'll take this omega and we will plug it into this equation and solve for VB. So VB equals negative L, which is 5, times the sine theta, which here is 4/5, times the omega, which is negative 1/6. And then we get 4 times the 1/6, which this is now 2/3, and the negative cancel. So VB equals 2/3 meters per second, which is basically 0.67 meters per second. And that is a positive. So we can, if we want to get vector form, VB equals 0.667 meters per second I hat. So let's just look at that and kind of let it soak in for a minute. Basically, what we did is we drew the triangle. We wrote the equations for the sides of the triangle, the x and y. Those were the position equations. We took the derivative, got velocity. We matched which corner corresponded to x dot or y dot. And then we had 2 equations with 2 unknowns, a velocity or a linear and an angular velocity. And so we solved out for omega and VB. So one point of clarification here, theta being this angle, as the ladder is falling on the ground, theta is shrinking. And so that's why our omega came out to be negative. But really, we need to pay attention to which direction is it going. So this negative, meaning that theta is shrinking, really our omega is going counterclockwise. So the better thing to do here is instead of putting that negative sign, we'll just say omega is 1/6 radians per second counterclockwise. Because normally counterclockwise is a positive value. The only reason the calculation came out negative is because we had defined theta from starting on the left side, the left direction of the x-axis instead of the right direction. And so that's why it came out to be negative, because this theta is shrinking. Whereas if we had made theta start from the positive x-axis, and so it was greater than 90 degrees, then it would look like it was growing. So we'll just say here 1/6 radians per second counterclockwise. And then the VB, the sign did come out correctly because the x direction was growing. And so, but we wrote this here in the vector form. And so VB is 0.667 meters per second to the right. So in order to solve for acceleration, we'll do a real similar thing to what we have just done here with velocity. And we will take the derivative of velocity, get acceleration, and then from there, we'll be able to solve out for alpha and AB. So we'll write down here, we will say step 3 is acceleration. Now we're going to have to use a product rule and a chain rule here to get this acceleration because we have theta, which is changing, and we have omega, which is changing. We don't necessarily know that omega is changing, but we can kind of guess it. And either way, we would take the derivative using product rule. And then if omega came out to be 0, then, well, even that doesn't tell us if it's a constant. So omega is changing. I'll just let y'all know that. So we need to use product rule when we take these derivatives. So to take the derivative of the x dot equation, we're going to get x double dot. And to do product rule in this, we take the first thing that changes is the theta. So derivative of sine theta is cosine theta. So we'll say negative L cosine theta. And then because of chain rule, a theta dot pops out. But we already had, we know theta dot's omega. There was already an omega there. So now it's going to be an omega squared. And then if we take the derivative of the omega part, omega dot is alpha. And so we'll just have the negative L sine of theta. And then that's going to be times alpha, which is omega dot. So this is the equation for the x double dot. Now the y double dot is going to be real similar. So using chain rule and product rule and chain rule on the y double dot, we know derivative of cosine is minus sine. So we'll have negative L sine theta. And that's going to be multiplied by omega, but also we have the omega that pops out for chain rule. And so we have omega squared. And then next we just take the derivative of the omega part. So plus L cosine theta times omega dot, which is alpha. Now, the x double dot equals acceleration of B, and the y double dot equals acceleration of A. But we were given in the problem that VA is constant. So that means that acceleration of A equals 0. So we will do the same procedure as before, where we take the y equation and solve for the unknown, which in this case is alpha, because we've already solved for omega. And so then we'll take that and we will plug it into the x double dot equation and solve for AB. All right, so we know that this has to equal 0 because acceleration of A is 0. So here we've got 0 equals negative L, which is 5, times the sine theta, which we got before was 4/5, times omega squared, which omega, we're going to still use the negative 1/6 because this is direction specific, but it gets squared anyway, and so it doesn't really matter. And then plus the 5 times the cosine theta, which is 3/5, times alpha. So now we've got all numbers for everything. We just need to isolate alpha. So go ahead and solve out and see what do you get for alpha. All right, so there's a question there on, is it positive or negative? What would alpha be? Well, or really what direction, is it going clockwise or counterclockwise? So the positive value from this calculation is correct to where the alpha value is positive, meaning that theta is not shrinking as quickly, or like the rate of shrinkage of theta is not as big. So alpha is going clockwise, which might be a little bit hard to visualize because we know that, okay, the ladder's falling closer to the ground, so theta is shrinking. Theta is shrinking, but remember that acceleration is how fast the shrinkage is changing. And it is not, theta is not shrinking as fast at the bottom as it is when you start at the top. Because at some point it hits the ground, it's not shrinking anymore at all. So the positive from this calculation is correct. And so what we end up with is 4/36 equals 3 alpha. And we rearrange, and alpha equals 0.0372 radians per second squared. And this will be clockwise. So the last step now is to solve out for AB. So the acceleration of B equals, and we just fill in everything from those equations. So we'll have negative L is 5 times the cosine theta, which is 3/5, times omega squared, negative 1/6 squared, minus L, which is 5, times sine theta, which is 4/5, times alpha, which is 0.0372. So put that all into a calculator and see what do you get for acceleration of B. Acceleration of B equals negative 0.232 meters per second. So this will be the vector form. This is going to be in the I hat because we know that B is going in the I hat direction only. So this negative acceleration means that B is slowing down. And that should make sense because B is going to be moving to the right really fast when the ladder is straight up. And by the time the ladder hits the ground, B can't go any further to the right. So it has a negative acceleration from the start to the end. All right. So this problem took a slightly different approach than we have done before, where here we just started with the position equations and we took the derivatives. And we did this in scalar form and not in vector form, whereas the cross product formulas is all for vectors. So the problems we did today, we use scalar equations for them. And so most problems, you can use either the vector or the scalar equations. The vector equations are nice because it is just a blanket formula that you start with that formula, you plug and chug. It is the same procedure every time of using those general planar motion cross product formulas. But sometimes it is easier to use a scalar equation if you know, for example, which direction things are moving, or like in this situation where we knew that point A was only going in the y direction. We knew that point B was only going in the x direction. So we could split it up into the scalar equations instead of having to use the cross product.